Good morning, sir.
Morning, sir.
Hello, sir. Good morning, sir.
Good morning, Balakrishnan.
She's spell his whole name. Good morning, Balakrishnan, sir.
Hello, good morning, Balakrishnan ji. Are you there? Are we audible to you?
Yes. Yeah. Good morning. Very good morning to all of you. Dr.
Very good
Ankush.
morning. Would you like to test your presentation once?
Yeah, sure. I will try to share. Give me a second.
We are just waiting for the participants. Mostly, they will be joining by 10. So right at 10 we'll start. Okay. You may just share. Just check once.
Sure. Like Professor, my screen is visible to you?
Yes. Very much. Okay.
All right. Yeah. Yeah. Initially, my I think a microphone was muted. I could not actually immediately respond to you.
Medium problem. So we have anchors. So first, at 10 they will introduce you, and then after a brief introduction, you will be on your way to for the presentation. We have roughly about 150 to 170 participants.
I see.
Slowly they will trickle in. Okay.
Perfectly fine.
Okay. So we just wait for 8 minutes to start.
Sure.
Thank you so much.
You are welcome.
A warm welcome and good morning wishes to one and all. Today we begin with the third day of the online familiarization workshop on 2D semiconductor nano devices and simulation as part of iNews I2I program. I am Ramkrishna Das Adhikari,
I'm Shipra Swal.
research scholar from Center for Nanotechnology, and we are the host for this morning session. This session will be recorded for an internal record, and we also request the participant to check the social media group for necessary updates. In the past 2 days of this workshop, a number of eminent speakers gave their valuable insight on the topic, such as 2D material devices, 2D material for nanoscale devices, and 2D material devices simulation. Today, our distinguished speaker for this session are Professor Vishwanath Balakrishnan, Michael Hart, and Mr. Anil Sharma. At the end of the talk, we will have a Q&A session, so the participant can drop their question in the chat box, which will be taken up by the speaker at the end of the talk. So now we begin with the first talk of the third day. This talk will be delivered by Professor Vishwanath Balakrishnan on the topic entitled Nano Manufacturing of Defect and Phase Engineered 2D Material for Device Application. Professor Vishwanath Balakrishnan is currently an associate professor at the School of Engineering, IIT Mandi. He obtained his BSc degree in physics from Madras University, followed by MSc in Material Science from Anna University. He was awarded a doctoral degree from the Indian Institute of Science, which is ISC, Bangalore. He has worked as a research associate at IISc, Bangalore. He has worked also as a postdoctoral fellow at Harvard University and a postdoctoral associate at MIT, USA. He has more than 60 publications in national and international journals. His research emphasis is on nano manufacturing for electronics, sensor, and micro supercapacitor application, nanomechanics of phase change electronics, material, and 2D material, phase transition in functional oxide material and thin film, also vapor phase growth like CBD, PVD, and ALD of functional nanostructures and thin functional nanostructures and thin functional nanostructures and thin
Hello, am I audible?
Yes, sir.
Okay, I think for some reason I could not actually listen
Yes,
your
sir.
voice earlier. Okay, I think for some reason I could not. Is there any like discontinuity? Am I audible?
Professor Balakrishnan, there was an
audible?
internet blip in the middle. Okay. So now we have restored. The audible, please go ahead. Internet blip in the middle.
All right, all right.
So now we have restored. The audible, please go ahead. Internet blip in the middle.
All right, all right. Yeah, let me just try to make my screen full screen. All right, all right. Yeah, let me just try to make my screen full screen. Yeah, let me first, thank the organizer for inviting me for this particular program. Let me first, I'm familiar with the INUP workshops, tutorials that has been going on in different places like IISc Bangalore, IIT Bombay, and also IIT Guwahati. And also thank you again for the research scholar organizers for a very nice introduction. Thank you again for since already he mentioned about some of our work. Probably I will quickly try to summarize before I start the actual topic. What are the research that is going on at IIT Mandi in our group? In brief, we are working on nano manufacturing, nano mechanics, and nanoscale devices. Because most of the cases, nano materials they are actually like known for their exotic properties. Most of the cases, right, a chemist as well as physicist, they have explored for several decades now. The main issue is when we want to really like take advantage of these properties, how much we can actually make these materials. Especially the topic here is a 2D material or any other functional material, for example. We need to ensure they are able to make a large scale so that there is a satisfaction in the industry to take this material forward. So that way, like making materials on a large scale without the compromise in the property and other parameters is one of the key aspects. In addition to that, when we make a nanoscale materials in a large scale, we also need to ensure how mechanically they are reliable. Most of the like semiconductor industries will have one particular division called reliability. So both chemical as well as mechanical reliability is another division called reliability. So we try to address this nano manufacturing, nanomechanics, and variety of functional materials, and also try to take some of these like key aspects, key materials to the device application. And also try to take some of these like key aspects, like some of the transistors, and also energy devices like micro supercapacitors and so on. There are three materials essentially we are focusing on at the present. First one is the phase change material. The vanadium dioxide is one of the, I would say, excellent choice of material if you want to understand the phase transformation, and also make many of the MEMS devices, nano cantilever, and also like multiple triggers you can employ in order to tune the properties reversibly, including for some of the switches. And memory application is still difficult, but there are some interest in the memristor applications. So though this material is actually like known from 1959, but essentially like not only just understand the basic physics of the phase transformation, large scale fabrication in the device geometry, and also reversibly tune the properties both mechanical, electrical, and optical. That is something of our interest. We looked at the phase transformation, looked at the microstructural investigation as well as the mechanical behavior. And the second aspect is something close to the topic that I have chosen today. That is also the interest for this particular workshop. And work I will be able to explain. There is some background noise. I think now it's I think all right. So the idea here is like large scale controlled growth of monolayers, and also we should be able to control both defects as well as phase. I think defect engineering in a semiconductor is known for several decades, but is it really possible to control the defects within the one atomic layer of 2D materials? And more importantly, when we introduce the defects for improving the properties, we also need to make sure the mechanical reliability aspects, like for example, fracture and so on, should not be compromised. The other aspect is, in addition to the phase, there is also a lot of interest in controlling the phase. In addition to the defects, we call phase engineering, because the 2D materials has many allotropic forms. For example, we know for the case of carbon.
Sorry, sir, Professor Balakrishnan. We see a black patch on your screen at the right bottom. Can you minimize that? Can you minimize that?
Is it now out of the screen or still?
It's now gone. Thank you, sir. Yeah.
All right, thank you. So so I was just mentioning about controlling the phase. The case of carbon, we know we have many allotropes, right? Graphite, diamond, based on the hybridization and so on. Similarly, the 2D materials, in this case, we are focusing on transition metal dichalcogenides. They also have multiple allotropic phases. The question is how reversibly and controllably we can tune this kind of phase transformation. And more importantly, some of the states are not really stable. We call metastable phases. Can we really stabilize these metastable phases in the 2D geometry is the another aspect. So at least we feel both the defect as well as the phase engineering, both of them essentially has a lot of essentially application if you are able to control them in a right fashion. The third aspect is we again grow carbon nanotubes. Starting from vanadium dioxide, 2D material as well as carbon nanotubes. Our main focus is the vapor phase growth, especially chemical vapor deposition. We grow carbon nanotube not only just like in the clusters, we essentially grow vertically aligned carbon nanotube up to 1 millimeter or even 2 millimeter tall. Try to understand the collective growth mechanism and also what is the surface interaction with the water and other electrolytes for making a supercapacitors and so on. So like just to recall, the topic is nano manufacturing of defect and phase engineered 2D materials for device application. So the question is, what is there for 2D materials? Of course, graphene got Nobel Prize. After that, people moved forward because graphene do not have the band gap. There are possibility of introducing band gap in the graphene, but otherwise, by and large, as such, the graphene is a metallic in nature. Whereas the transition metal dichalcogenides receive a lot of attention because of the semiconducting nature. As such, the bulk, many of them are showing a indirect band gap. But the moment you make it as a single layer, they essentially show direct band gap, which is making them very attractive for optical, optoelectronic applications and so on. So this is a very nice, image. I think appeared in the review article written by Professor Ram Gopal Rao and his group from both IIT Delhi and IIT Bangalore. What is very interesting about this particular figure is, I think this figure is actually known for several decades earlier. For any new invention or any new discovery, for example, immediately you would see initially there will be an innovation trigger we call. There will be a lot of essentially expectation. There will be a lot of hype and so on. You will see there is a media is talking about Nobel Prizes and so on. There will be a lot of attention. Where initial discovery, a lot of fundamentals are also explored and so on. But the application may not be realized. But after some time, it will reach a peak. This peak probably it is true for when the carbon nanotube came. People thought carbon nanotube will replace the silicon. Same when the graphene discovery happens also, there is a huge amount of hype. Same with the superconductivity, people thought, the newspaper, the first page it will appear. The superconductivity, the energy problem for, the world would be solved and so on. But eventually, there will be a peak where essentially people start seeing the expected outcomes are not reaching. There are actual, difficulties, especially when we want to convert your basic, innovation into actual product and devices. There will be a disappointment that we call essentially it's a valley of death, because here, whatever initial hype, it is not meeting the actual deliverable. Of course, in many cases, it will take around 20 years and so on. Then essentially in the valley of death, otherwise you can call trough of disillusionment. That is where the industry essentially comes in and try to see how do you address some of the issues in terms of fabrication, especially large scale fabrication, and also try to show actual devices and so on. So for 2D materials, initially you can see starting from graphene, then large area growth, many of the 2D materials one by one. There is a big periodic table talking about thousands of 2D materials possibilities and so on. And also a lot of physics, interesting properties for several applications also initially reported. Then people started talking about how do you make wearable devices, flexible devices, try to do heterostructure growth, and more importantly, look at the contacts with the different 2D materials and so on. Then eventually there will be a kind of a linear increasing trend where we see a clear prototypes and at least if not products, at least prototypes in some level of satisfaction. It is possible to make devices. Can be a sensor, neuromorphic processors, many of the flexible electronic devices and so on. So right now we are somewhere in the 2022. By 2028, already there are many papers. If you look at the IEEE transactions, There are several products already like a plan for 2028 based on transition metal dichalcogenide based 2D materials. In fact, eventually, what is the vision, envision for 2030 and further? Already, lots of discussion is going on about quantum technologies, quantum materials, right? This is also one of the identified candidate for quantum computing with respect to qubits and so on. So that way, there is a like a definite vision and also growth. Somewhere we are already in this right at this particular location, where there is a realization of many of the fundamentals discoveries possible in terms of product development in the near future. So the same thing, I also quickly try to look at the literature, the 2D materials. If you take any of the search engines and put the combination of 2D materials and chemical vapor deposition, you will see the number of publication essentially shoots up. It's, I think, invariably true for many of the other materials as well. The publications keep on increasing. Somewhere like around 2014, there is the onset. Clearly, the trend is increasing for 2D materials and the combination of CVD growth. But the same thing, if you try for the actual research publication from India, it shows the same trend. It is shooting up. But the problem is we are almost like 3 years late. In international community, somewhere 2014, the trend is essentially set, whereas in India, it is set only in 2017, which means almost like 3 years, we are essentially lagging behind the advanced countries. Of course, China and the US competing for the first place. Sometimes Korea also comes in third. India is, I think, fourth places in many of the research, right, publication, but we are still 3 years late. And more importantly, if you look at the publication number, here it is like a few hundreds in number, whereas few tens in India. So both in terms of right at time, as well as in terms of the actual quantity, there is a gap. When you speak in terms of product development or device fabrication, the gap is even much larger. That is where I think this kind of workshop, especially like focusing on nanotechnology and device fabrication, especially focusing on 2D material, would be more relevant to promote more research in this area. Another aspect of 2D materials, in addition to the projected roadmap, of course, there is always a debate whether silicon will be replaced by 2D materials and so on or not. But I think there is a clear understanding it may not replace the silicon because silicon technology is well established and the fab lines we may not be able to that quickly change. More importantly, whatever the knowledge gain and the state of art, the technology is developed, it may be much more wiser to add the 2D materials along with the silicon and other technologies. And that is what mostly like people are talking about integration of 2D material with existing semiconducting wafers and so on. But one aspect is the flexibility. Many of the electronic devices now, optical devices, for example, or televisions and so on, everything is flexible. More importantly, now the wearable devices become also very common, including textile industry. Now they're talking about how do we make wearable electronics. Same way, sensors, especially the biosensor, the actual projected demand is huge. Now, like we have reached a stage, not even a wearable, because wearable at some time, I'll wear a particular cloth, tomorrow it will be a different cloth. So it may not be that compatible. Now people are exploring how do you make a wearable, essentially a skin mountable sensors, biosensors, which can essentially 24/7 monitor your body parameters. At the same time, it will be like just like a tattoos. We don't have to really worry about taking care of the the wearable devices and so on. So that way, like at least for last 7-8 minutes, what I'm trying to convey here is there are a lot of scope in the 2D materials in the overall development of semiconductor application, both in terms of like a smartness and a lightweight, and more importantly the flexibility. There is a demanding application by 2028 onwards. I think there will be a product where we can actually appreciate some of the research that is gone for last more than a decade now. So these are some of the issues also I'd like to address, like that is what in our group we do, defect and phase engineering. How do we do a controlled growth of 2D materials? And during the CVD growth itself, if we can control the defects, that will be more interesting. And further, like in addition to the controlling the defect, we can also like make sure how the defect introduction enhances the properties. For example, optical properties and also the.
Sir, your screen is not visible.
Your PPT is not visible, sir.
Yes.
Oh, I see. I think there was some change happened in the screen for a moment came up. Maybe I may have to again share.
It's coming now, sir. The black patch is there. You can minimize that.
All right. Yeah, so I think I am audible and my screen is visible.
Yes, sir.
Right. So I was just mentioning about controlling the defect and also ensuring that we have an enhancement in the properties. Both are important. And the third aspect is when you are actually like introducing a defect, probing the defects, especially we are talking about atomic defects like sulfur vacancy or tungsten vacancy in the case of WS2, are replacing some of this, like either chalcogen atom or the metallic atom with some other right atomic species. That way, the probing the local defects also will be a very difficult task. And when we have a defects, at least we feel the defects and the phase, the allotropic phases, they have a lot of correlation and connection. Identification of phases, especially we call 1T, 1T prime, 1H, and even 3R and so on. Many of these phases are actually known in the bulk system. As such, in the one atomic monolayer, how the phase stabilization happens, the complete characterization is also like, there are some ambiguity and more work needs to be done. And I'll give you like a few examples for, like a defect reconstruction. How do we control the polymorphic phases in 2D materials? And is it also possible to even, we have a WS2, for example, we have a tungsten sandwiched between two sulfur layers. Is it possible also to remove selectively some sulfur, right? We call atomic stripping, how that can be, achieved and also exploited for enhancing the properties and so on. I'll also show you some of the FET and photo conductivity measurement. If possible, I will show you some memristor as well as supercapacitor application. So when I say defects, I think it's a basic materials or like solid state physics. Most of you would be familiar. We may have a vacancies, essentially like sulfur or a metallic atom. Typically, there is a difference in a say MOS2 or WS2. It is much more easier to essentially like introduce a vacancy of sulfur compared to the metallic species. The reason being the formation energies. The sulfur binding energy is only 1.2 electron volt, whereas tungsten, for example, in the case of WS2, it's around 6 electron volt. So it's much easier to remove the sulfur. But once you start removing the sulfur, eventually the chain get affected. You would be able to remove the metallic species as well. So that way, the absence of your any of your atomic species we call vacancies. And also there are a lot of interest in creating disorder structure. Now people are talking about, can we make amorphous 2D material like a glass-like 2D materials and so on. One aspect is already we know high entropy alloys are gaining a lot of attention. Similar like efforts also being done for introducing disorder in the 2D materials. Again, selective dopants, and of course edges are almost always it's prone to attract things from outside. That way, like your edges are always active. You may also have a grain boundaries and interfaces, especially when you make a planar heterostructure. Otherwise, in plane heterostructures, these kind of interfaces also we can find out. It is also possible to make vertical heterojunctions. People have reported at the interface, right? There are like you have a clearly enhancement of photoluminescence and so on due to the interfacial excitons. So it is possible to have this kind of common defects in the 2D materials, and many of them it is also possible during the actual growth itself. What I mean by the phases, I was talking about the allotropic phase or phase engineering. And just one quick slide. In a 2D material, especially if I take say WS2 as an example, as I said earlier, we have a one monolayer essentially has 3 atomic layer. Unlike graphene, graphene is just a one carbon. When you say monolayer, it is only a, like, have a hexagonal arrangement of carbon atoms. In the case of WS2, we have a tungsten layer sandwiched between 2 sulfur layers. So that is what, like, most of the cases during the CVD growth, the WS2 forms in the, right, like we call 1H phase. 1H phase are like, nowadays, like there was confusion between 2H and 1H. Typically, like to have this particular, the structure, hexagonal structure, you need to have a 2 unit cell. That is why we call 2H. But now it is possible also, people are saying we have only one layer. So that is why there is a confusion between the bulk crystallography and the monolayer crystallography. Then it is many of the literature also now changed to 1H. So that is a semiconducting most stable phase you will find for many of the 2D materials. However, it is also possible to introduce small amount of gliding. Imagine you have the top layer or the bottom layer of sulfur slightly glided, which means the top layer of sulfur and bottom layer of sulfur will not coincide in the same position. That way we can actually like achieve other allotropic phases. That is what happens in the case of 1T phase. 1T phase is metallic. Then you can also have a gliding plus small amount of distortion in your bond length. Then we call distorted 1T, otherwise 1T prime. It is essentially semi-metallic phase. So like we can have a metallic, right, insulating or a semiconductor and a semi-metallic, all of them just by essentially manipulating your, right, in the form of but as I mentioned earlier, many of this phase engineering has a direct link with the defect. That is why, like, during the synthesis itself, if we can introduce some defects, it is also possible to stabilize what is otherwise not, stable at room temperature, like 1T phase or 1T prime phase and so on. In terms of phase engineering, there are reports we can stabilize the 1T prime or 1T phases by applying the stress. In this case, it is done with the, like a force. With a high amount of, either strain or stress, you will be able to stabilize 1T prime phase. In the CVD growth, it is also possible to stabilize this 1T prime phase. There are two possibilities. One is during the cooling, right? You do a fast cooling so that, kinetically you can control. And the other possibility is by changing the growth parameters. It is known that when we have a hydrogen, typically hydrogen we use in order to have a reducing atmosphere. With respect to hydrogen content also, it is known we can introduce the 1T prime or 1T metastable phases can be stabilized. Just to give you a brief idea about the a CVD growth, how do we grow CVD, 2D materials, especially in large scale. Of course, we have a MOO3 or WO3. There are multiple possibilities. We can use many metallic precursor. So typically in our group, we use oxide precursor, say MOO3 or WO3. We keep it as a high temperature zone. The growth temperature would be say around 850 degrees Celsius. And sulfur, undergoes sublimation. Melting point is also very low. So that will be kept at low temperature zone around 200 degrees Celsius. Then we have a argon, hydrogen, nitrogen combination. It is a kind of a mild reducing atmosphere where your MOO3 would be decomposed and reduced. Then the reduced molybdenum would be sulfurized with respect to the sulfur flow, right? So essentially this molybdenum and the sulfur essentially reacts together and forms the MOS2 in the silicon substrate. In the case of WO3, tungsten and sulfur reacts together and forms WS2. Instead of keeping this kind of oxide precursor or powder, it is also possible to do the MOS2 or WS2 growth by depositing, say, do a DC sputtering of molybdenum or tungsten initially as a metal. Then you can do a controlled sulfurization. All we need to do is we need to provide two species. One is the metallic species. Second one is the chalcogen atoms. Then essentially they undergo the reaction. Of course, in terms of 2D materials growth, we need to also make sure that the flow is also important. The flow rate, right? We don't want to have a turbulent flow. Kind of a laminar flow is important. Of course, we need to look at the Reynolds number and so on. Based on the tube diameter, the right flow rate has to be adjusted. And the second aspect is the concentration of the precursor also important. Very high concentration, typically we'll have a, like a vertically kind of three-dimensional growth will take place. You would not get the actual 2D growth. Typically 2D growth, right, where the advancement of the edges, right, your growth interface has to move laterally on the surface. So that typically happens at the relatively low concentration. So this is the one example where we can see like we are able to grow at least millimeter scale CVD growth of WS2 monolayer. The background you have an optical microscope image. Whatever you see here, all of them are essentially like if you zoom it, you will see this kind of flakes like 100 micron, 200 micron flakes. Unfortunately, it is still, I would say, not continuous. You can also see a backside, the pinkish color substrate. That is a silicon with a 300 nanometer of thermal native oxide. So it is not continuous, but mostly like it is a flakes. If you are lucky in some areas, maybe you can get for a maximum of 1 millimeter continuous region is possible to get. But we are trying to work further to make at least, like in a centimeter scale, we can make continuous this kind of 2D materials by, like adopting different growth promoters and so on. Just to like, avoid the confusion about the quality of the material, I'll only show one slide quick characterization. After the growth, we need to ensure it is a monolayer. So we look at in the optical microscope in FESEM just to get an idea about the lateral dimension. Then do AFM to confirm the monolayer. Typically, it's around 0.8 nanometers for the WS2. Then we also rely on, more importantly, Raman spectroscopy as well as photoluminescence spectroscopy. Especially in the photoluminescence, instead of monolayer, if it is bilayer, you can see the effect here. The blue color essentially shows the emission at 1.93 electron volt for the monolayer. But the moment you have a just addition of one more layer, just a 2 layer, you will see there is a small shift in the peak position. In addition to that, you see almost the PL is getting quenched because there is a transition from the direct band gap to indirect band gap. Starting from third layer, you would not see any emission at all, right? That is because of the direct to indirect band gap transition. We also do the PL mapping just to make sure, right, there is a uniform monolayer present in our case. I'll give you like a 3-4 cases where the manufacturing can be done in a controlled way towards the some, like enhancement of the property. So like many cases, as is shown here, you will have a triangle or truncated triangle, some cases perfect hexagon. So when you have a perfect hexagon or truncated triangle, essentially we end up having 6 edges, right? The edges can have a different termination. It can have a tungsten termination, or it can have a sulfur termination, or in some cases, you can have tungsten termination in one edge, sulfur termination in other edge. So what is interesting is when we have this kind of a sulfur and a tungsten termination alternatively, we can clearly see particular edge, right? It is a fluorescence microscope image. It is actually more active. The emission is not uniform in all the edges. It is right enhancement at the edges are known, but only particular edge is actually more active for the emission compared to the adjacent edge, right? That is we are trying to see there are some literature why it is happening and so on, because when you have a like a tungsten termination, right, you can also like how oxygen, as I said earlier, edges are prone to attract the right any adsorbed species. So the oxygen can essentially preferentially can absorb. Then oxygen can also induce a p doping. Essentially, it converts some of the trions into exciton. In some cases, even produces biexcitons. That is the reason you have a enhanced emission at the interface, especially at the terminated edges. So there are several methods to make this kind of edges by laser, electron beam, and also plasma, and so on. There are some reports showing this kind of like electron beam induced how the voids are created, and also like very carefully looking at the void termination, but they could not correlate that with the actual enhancement. But there are papers which also correlated with the enhancement. But the question is, in terms of manufacturing, making these kind of voids, right, or producing this kind of edges by electron beam and plasma, it is very expensive. Can we produce a much more simpler method? So what we have done in our group, we have first initially grown the 2D material, so typically like a WS2 in this case. After that, we essentially in the process introduce only 5 minutes or 10 minutes post-process growth of annealing. Typically, it is the argon hydrogen, right, annealing. During annealing process, what happens is, as I said earlier, the sulfur vacancies can be easily introduced because sulfur binding energy is much more, right, lower compared to the tungsten. Once you remove the sulfur, these kind of point defects, they can come together and form a kind of a void. We say essentially defect clustering and reconstruction essentially results in this kind of nice faceted voids. So that is what's shown here. I'll show you like how do we know it is void, how do we know the termination. We use aberration corrected microscope, in this case STEM in a Hadoff mode. We can see these are your tungsten and sulfur. Of course, sulfur atoms are not visible in this image. We can clearly see a void here. And again, by EDS mapping, we can confirm clearly it is a void. And we can also clearly see in a high mag image, there is a point defect. So these are the defects. When we have more and more of these defects, they cluster together and contribute for formation of faceted voids. Again, we looked at the kinetics of the faceted void formation by systematically changing the annealing time. 5 minutes, you have almost a perfect 2D material. In 15 minutes of post growth, you see small voids formation. And as a function of time, 30, 45, 60, and 90 minutes, almost your 2D material is completely thermally etched. We also made a clear process window. If you want to get 2D material without defect, so this is the profile for a given particular a temperature of 850 degrees Celsius. Somewhere around you can see 60 to 70 minutes, the growth essentially saturates. After that, if you keep it further for 10 minutes, 15 minutes, what will happen? Your growth will not further increase. Rather, your void essentially keep growing. So you can see void growth is increasing and WS2 is decreasing. These two are essentially complementary in nature. Again, we looked at the termination by looking at the Hadoff imaging more closely, tungsten termination, sulfur termination, and so on. And we are also able to look at PL mapping, clearly correlating your termination. And again, oxygen we are not able to clearly capture in the imaging, but we do get the signal of oxygen when there are papers talking about WS2 minus X. Some sulfur is replaced with the oxygen. They call oxysulfide and so on. Very, very small amount, but we can clearly see the enhancement in the PL signals. And then we thought, is it also not possible to produce this kind of voids in a very selective controlled way? Because when we are doing annealing, we have no idea where the voids are going to form, right? The defects essentially will take over we human being or anybody trying to control them. Then we thought, can we use nano indentation technique to selectively do a nano sculpting, right? So nano indentation is a very simple technique to measure the mechanical behavior. It is a very sharp diamond tip with the application of force. We can essentially touch your 2D material, and with the increase in further load, we can selectively make a sculpting. And since it is a nice 2D transducer, we can make any pattern that we want. We can select the position. We can also select or change the actual load or the stress involved. So we are able to do this kind of selective sculpting by the arrays of nano indentation. Then again, we can clearly see that the PL, the optical signal can be modulated based on the pattern that we draw. These are some of the examples where we have written IIT by the nano indentation. Accordingly, you can see in the fluorescence imaging and PL mapping, the optical emissions are easily can be manipulated. The third aspect, I think, what I want to cover is, in addition to the defect, right, and the fabrication, how do we control the phase, different allotropic phases? Again, that is also possible to achieve by CVD. This is an optical microscope image of the WS2 monolayer. We don't see any contrast. But if you see in, I know, like in a fluorescence image, we are essentially seeing this kind of contrast where we have a, self-organized alternate triangles. One is dark, one is bright, again dark, light. So this is again we are observing from very, very small size, even like, like less than a micron, right? And we have seen in the confocal microscope to some extent. But clearly, like after a few microns where we are able to resolve, there is two different contrasts emerging and growing as a function of time. But when we try to do a line profile analysis using AFM, is there any difference in the thickness? Because immediately when we see optical contrast, we thought maybe this is a bilayer, maybe this is monolayer, bilayer probably because of indirect band gap, not emitting. But absolutely we don't see any thickness contrast, thickness variation across the interfaces. Right? Then this is what I was talking about, the fluorescent microscope image. If it is only 1H semiconducting phase, you will have a uniform intensity across your flake. But when we have a biphasic or 1H 1T prime, you have a varied intensity, and also spatially they are very nicely organized in the form of triangles. Then we are calling 1T prime because the intensity in the PL, it is not zero. If it is 1T, it is metallic, you wouldn't get any signal. Since we are getting a signal almost 50% or 40% of your semiconducting phase, we are thinking it is a semi-metallic having a very small, in this case semi-metallic, it is not a zero band gap, there is a small amount of band gap. Rather than saying semi-metallic, we should say probably very, very small semiconducting gap. That is what promoting this kind of a low intensity emissions. And again, when we looked at the PL profile, we can see like going from one phase to another phase, there's a huge jump in the PL enhancement, right? PL intensity. Not only the PL intensity, we also looked at the lifetime, because intensity is an extrinsic, right, parameter. It can vary due to many, right, reasons. Whereas the lifetime, fluorescence lifetime is something intrinsic characteristic of the semiconducting material, like quantum dots and so on. We looked at the lifetime imaging. Again, we see a contrast between the 1T prime and 1H phase. And there is a 3 times of difference in the lifetime. 1H phase has around 3 nanoseconds, whereas 1T prime has a 1 nanoseconds of lifetime. Lifetime, I mean, when the light falling on your semiconducting 2D material, there is a exciton created, right? Electron hole pair created. What is the actual typical lifetime of this, right, exciton? That is what we are trying to capture. Again, in order to get a clear confirmation of the phases, we have done the atomic resolution, in this case, right, annular dark field STM imaging from the same flake to different triangles that we discussed earlier. We can again clearly see the small distortion that I talked about. We get some indication of sulfur. As I said earlier, if it is a 1H phase, you will get only one sulfur position, whereas in the 1T prime, you have a small distortion in the sulfur that we are able to capture in the aberration corrected microscope imaging. Further, we also connected this allotropic phase stabilization, because in the literature it is known T prime phase cannot be stabilized without having any stress or strain, or at least impurity doping. In our case, we found that there is a huge amount of sulfur vacancies, especially like these kind of biphasic structures. Sulfur vacancies are there, there is also evidence of tungsten 6+, which means there is also a small amount of oxygen. So the sulfur deficiency and the oxygen incorporation that seems to help in stabilizing these kind of metastable phases. We also looked at the KPFM because we want to know any surface contact potential properties. Is there any difference we could observe? Again, we are observing around 40 milli-electron volt of difference, contact potential difference between your 1H phase and 1T prime phase. We made a transistor, and more importantly, in a transistor, we want to see the photo conductivity, especially if you want to make a photo detectors and so on. We want to have a good semiconductor. So we have done in this case photo detector or photo conductivity measurement from a one flake. Again, by electron beam lithography, we make a device. We know this particular facet. This facet is 1H phase. The smaller facet is 1T. Right. So by looking at the both optical imaging and the fluorescence imaging, we identify. Then try to see when you shine a light how the current is changing. What we found was compared to the 1T prime, the 1H phase shows 5 times of larger photocurrent. That is what initially shown here. Dark condition eliminated. The last one shows the difference. The actual photocurrent, otherwise the difference between the dark current and the light illuminated current, that is 5 times higher for semiconducting 1H phase, whereas 1T prime shows a very, very weak photocurrent. Again, that is also clearly, helping us to understand the actual, the semiconducting nature and the semi-metallic nature. We can also make devices because we have in a one monolayer, we have two different phases, right? So it is easy to make devices and by adopting the routine electron beam lithography as well as plasma etching, we made varieties of patterns. Probably I will skip for the benefit of time. In addition to this, as I mentioned earlier, if the sulfur deficiency is extremely important for allotropic stabilization, we also wanted to find out if we do change the precursor concentration, right? We can make a CVD reaction depriving the sulfur, which means you are not putting enough sulfur compared to what is required to make a stoichiometric WS2. So by doing that kind of deprived reaction, we are able to see the growth when happens, right? We have to be honest here. The tungsten I told you will be better sandwiched by the tungsten, better sandwiched by the two sulfur layer. But in the deprived condition, we are able to see the sulfur top layer or bottom layer, they are really, really defective because we don't have that much of sulfur to produce a stoichiometric WS2 monolayer. In those kind of condition, we are able to get almost one layer. It may not be complete layer is stripped off, top or bottom, randomly many sulfurs are removed. So we are able to see that in this case, we have a 2D material monolayer. This kind of deprivation happens from the center. So we have a sulfur deficient, heavily sulfur deficient region in the center, and hello.
Yes, sir.
Hello.
Yes, sir. You are audible.
I'm audible.
Yes, sir. Yes.
Okay, I hope my screen is visible.
Yes, sir. But there is a black patch.
Oh, I
Yeah.
see. Okay.
Okay.
Yeah.
Okay. It's not fine.
I think sorry for the internet trouble. So like I was just trying to explain, when we have a deprived condition, when we have a small amount of sulfur precursor available for the growth, we end up creating in the heavily, or severely sulfur deficient region at the center. We want to see how this kind of, sulfur deficient region going to contribute or affect the properties. Again, the sulfur deficiency can be even seen in the optical contrast. You see in monolayer, right, there is a difference in the optical contrast. We also looked at the AFM, though it is very close to the actual, the measurement limit of the AFM. We do see some difference in the height. right? Compared to the side, the center, we can see the height is essentially also lower, right? Indicating that there is some removal has taken place. Interestingly, compared to the other regions earlier I am talking about, the 1H region, 1T region, that variation we know. But if you look at only in the center region where the sulfur is severely defective, there we saw almost 20 times of enhancement in the photoluminescence, which means the sulfur after striped off or like one layer, close to one layer at least, we can see more and more absorption of oxygen is possible. As I said earlier, whenever we have oxygen absorption, right, they essentially can induce a lot of biexcitons. That is what probably the PL very closely. The difference between 1H and 1T prime, earlier what we observed, compared to that, it is much more higher enhancement when we have a severely sulfur deficient 2D materials. Again, we confirm that no sulfur defect, and also we try to quantify and so on. Right, there is a clear evidence of sulfur deficient. Sulfur deficiency essentially introduces small change in the your binding energy in your XPS. That is something consistent with the literature. In addition to that, we also see an emergence of tungsten 6+, right? Tungsten 6+, meaning there is also clearly oxygen coming and binding with the tungsten, making it is going from 4+ to 6+. Based on this, we know it is a sulfur deficient and also possibly absorbed or substituted by the oxygen. When we are talking about defects, a lot of point defects, I also earlier mentioned, we also can introduce this kind of voids, the voids as like an enhancement in the emission. But the question is how mechanically reliable structures we are able to produce when we keep on increase the defect concentration. So this is a one extreme case. When we introduce more and more defects, we have lots of this kind of voids. In addition to these voids, you can also see almost like a spider net. All these voids are connected by the crack, which means after the growth of CVD or during the cooling process, your 2D materials no longer going to be intact, rather it will be severely fractured, right? The actual point defects and the voids are acting as the culprit for the fracture. At the same time, your thermal mismatch stress between the substrate and your 2D material, that is essentially imposing the thermal stress. What we found is, interestingly, this kind of fracture happens when we have a 1H phase. But if you have a 1T and 1H phase, the mixed phase, the in-plane heterostructure, right, even if you have a defect, still we don't see this kind of fracture. That was we are kind of, really, it's a counterintuitive. Generally, we think heterostructures are prone to the, strain and so on. In this case, heterostructures are more stable compared to the only homogeneous structure. Then we carefully looked at the Raman spectroscopy and found that because of the 1T, 1H coexisting phase nature, intrinsically this 2D material, biphasic 2D material, has some compressive strain. How do you know that? We know that by looking at the Raman spectroscopy, there is a consistent shift. So because of the inbuilt compressive strain, when there is a thermal mismatch strain, typically you need to have a tensile stress in order to induce the cracking and fracture. When there is a thermal mismatch stress, tensile stress, then the inbuilt compressive stress in this case essentially balances. That is what essentially stabilizes your heterostructures compared to the homogeneous 1H structure. Again, we want to also see how we can, avoid. In some cases, we may want to have the void, we may want to have a defect. Same time, is it possible to avoid the cracking? For that reason, we did a kind of a thermal stress engineering by changing the different growth substrate. We have chosen essentially like a 4 substrate. WS2 we have grown on sapphire, quartz, silicon, and SiSiO2. You can see here the arrow marks are shown here based on the right your and the actual spectroscopy. The WS2 on sapphire essentially has a compression, whereas WS2 on quartz, silicon, and SiSiO2, in fact SiSiO2 is the worst, has a huge amount of tension. So when you try to grow WS2 on SiSiO2, it is very easy to get fractured because there is a huge amount of thermal mismatch stress. Especially the nature of the stress is tension. Whereas in the sapphire, you will have a compression. In the compression, you will not have a fracture. If at all, you would have some buckling may take place. So we have clearly looked at fracture, severe fracture in the case of silicon and SiSiO2. No fracture in the case of sapphire. Even if there is a void, if there is a sapphire substrate, you would not see any cracking taking place. Again, we have looked at the microscope, right? We also did the basic about the simulation, FEM simulation, right? And also abacus and so on to understand how the stress or strain is distributing around the void. We looked at the both the thermal mismatch stress as well as the distribution around the void. Again, you can see in a WS2 on sapphire, it is a compressive in nature. So you will have a slight curvature in your void, but it will not crack. Whereas in other cases, the amount of stress is huge. Almost we are talking about 0.7 to around 1.2 gigapascal of tensile stress contributing for fracture. In addition to that, it is not only the stress is important, the load transfer will happen based on your interaction. It is also found that WS2 on sapphire, right? They're essentially very weakly bonded. When it is weakly bonded, again, your thermal mismatch stress will not make a big impact. Whereas in the case of silicon and SiO2, the bonding, I mean, the adhesion between WS2 and the substrate is huge. Again, that is also one of the reasons why there is a cracking in the case of silicon or quartz. I think I'll skip some of this. This is essentially for a flexible application. We have done the, applying different orientation, right? The tensile test and showing the fracture behavior. For a fabrication, I'll quickly show, maybe in a couple of minutes I may have to finish. It is also possible to introduce heterostructure formation in the CVD. It is very simple. First you finish to MOS2 growth. After that, do the regrowth. You essentially introduce the WS2 growth. So because of the edges already present and WS2 and MOS2 also have almost very identical lattice parameter, we can get planar heterostructures. Earlier planar heterostructure, it is chemically same, only the structure is changing. But in this case, it is chemically also different. This is WS2, outside is MOS2. Again, we are characterized in order to show that. Only one point is, yeah.
So, excuse me, sir. So we have only 5 more minutes. 5 minutes.
Sure, I'll finish in 2-3 minutes now. So the heterostructure when we make, we see a lot of excitonic emissions at the interface compared to the MOS to WS2 region. Again, justifying why heterostructures, right? We call defect bound exciton and so on, right? Whenever we have a heterostructure at the interface, there is a possibility of creating, or the exciton can be localized. The other aspect is, in some cases, we can also use fractured 2D material and try to again do atomic stitching, right? If, for example, here there is already a fracture, WS2 is broken, then we do a regrowth, the fractured, wherever the crack is present, there the MOS2 essentially grows, not only grows, essentially stitches these broken bonds of WS2. Again, we have characterized very carefully and also looked at in the aberration corrected microscope. Probably we have found some interesting results when we have this kind of atomic stitching, both optical enhancement and also the contact potential goes up. Probably like a lack of time, I may not be able to complete. It is also possible to make, by mixing with the carbon nanotubes and so on, we can make memristor devices with using 2D materials. We are currently working on both memristor as well as supercapacitor. Especially one of the idea for supercapacitor is when you are using 2D material, especially direct band gap 2D material, can we also use light to charge the supercapacitor? So otherwise, at least what is the effect of light on the charging discharging behavior of the supercapacitor? That is also we are looking at it. So these are the students, the PhD scholars who has actually done the work. I was only presenting for last 1 hour. I really thank dedicate like the entire talk to the scholars who has put really sincere efforts. We also have a good lab including CVD, many CVDs we have, ALD, sputtering, photoconductivity, and nano-inundation. I mean, just to summarize, I would say the CVD growth provides a lot of opportunities to engineer to achieve large scale growth with the provision of engineering defect as well as phases towards enhancing properties for many of the newer newer properties and application. Hopefully, like in the coming years, when the products are coming out, more and more probably would be able to introduce many of these defects and manipulate them further towards improvement in the actual devices and so on. So I'll stop here. If there are any questions, I'll be happy to answer. Once again, thank you for inviting me, and thank you for your attention. Thank you.
Thank you, Professor Balakrishnan, for your insightful talk. Now we begin our question and answer session for this topic. So our first question asked by Rameshji. The question is, how does single layer is responsible for metal dichalcogenide to have direct band gap? Can you please explain this with the EK curve?
Yeah, so like you are saying, why the monolayer has the direct band gap?
Yes, sir.
Yeah, so I think this is well reported as somebody was mentioning about E versus K curve. Essentially like a direct band gap and indirect band gap, essentially the electron transfer, if it is a direct band gap, we don't have to have any momentum. Without any change in the momentum, direct transfer can happen. Of course, this whatever the landscape of your whatever the parabolas you see, whether the valency band maximum and conduction band minimum happens for the same value of K, extremely sensitive to your lattice spacing. That is why it is possible by essentially changing the lattice spacing by applying stress or strain, it is possible to manipulate the band gap, even cases where we can achieve direct to indirect or indirect to direct. Same way, when there are defects, again you are locally going to introduce some dopant level or impurity levels. Again you can change the maxima minima, you can change the band gap. In this case, what we are doing, we are going from a bulk to the monolayer. What is happening is, of course, one is the quantum confinement. We all know when you reduce the size, band gap increases. In this case, in the band gap, not only the increases, your maximum minimum portion also changes. In brief, we need to look at the size reduction when we are going from the bulk to the monolayer, the quantum confinement, along with the actual the landscape, the position of the minima and maxima, that essentially overlaps. Overlaps in the sense for a same value of momentum, you will have it for the monolayer, we call direct band gap. In the case of indirect band gap, of course, it is displaced.
Thank you, sir. So the second question is there any threshold force for nanosculpting by nano indentation for 2D material?
Yeah, threshold, I think you mean by that the load, of course, the nano indentation, smaller the load, like it is better because we can achieve a very, very small void. The technique as such, we can control the load from the prescription shows 70 nanonewton, but I would not rely on it. At least 1 micronewton to maximum 10 millinewton. In fact, in one of the slides I have shown systematically we have changed the load. Accordingly, we can also achieve different sizes of the voids. If you look at here the arrays, the one it is not even visible, the first array, right? This is for an incremental load. We have gone from very small load of somewhere around 25 micronewton to maximum load of around millinewtons. Of course, you can choose based on the substrate, how much you want to deform and so on. The threshold, like I would say, the difficulty would be if you are doing in a freestanding. The freestanding doing the nano indentation there, I think it would be very interesting, but we have not tried so far.
Thank you, sir. The next question asked by Krishnam Raju. The question is in slide number 16. The x-axis scale is different for all images. Why it is not uniform like 50 nanometer or 5 nanometer?
X-axis. Oh, you mean the SEM images? Yeah, I think the SEM images I can see here, like some of them are 50 micron, some are 30 micron. So just to clarify, we are not looking at the same sample. These are different growth, different flakes, right? Different growth experiment. In this case, we have done the growth, otherwise post-growth annealing 5 minutes. In another growth, post-growth annealing time is changed to 15 minutes, 30 minutes, 45 minutes. Since we are looking at the different samples, to get the same area, of course, imaging can be done with the same magnification, but we want to cover both what we are looking for. In this case, we want to look for the more and more number of whites and area of whites is increasing. I think I agree with you. It can be done for a same magnification. Since it is a different sample, we want to show overall the population as well as the aerial coverage. That is why we have done this. Otherwise, you are right. It is possible in principle, can be done for a same magnification.
Thank you, sir. The next question is, how would be the defect be with the PVD like evaporation?
Can you please repeat the question?
How would be the defects be with the PVD like E-beam evaporation?
Okay, E-beam evaporation. Okay, E-beam evaporation is a technique we use it for deposition, right? So in this case, defect, I am not able to. Okay, maybe you are talking about E-beam induced defect creation. The literature that I have shown, what they have done is they have used TEM. I think if I take your question, can we use electron beam that we are using as for a lithography? Whether that can be used to produce kind of defects? The answer is yes, but it depends upon your voltage. Typically, like we know for graphene, in order to remove the carbon atoms, we need to have somewhere around 80 kilovolts. For 2D materials, I need to check what is the exact number required. So as long as your threshold voltage is sufficient to knock out the sulfur, of course tungsten would be much more difficult. At least to sulfur, if you are able to remove, then definitely it can be done with the E-beam as well. Right, so in this case, TEM is relatively easy because TEM is operated at around say 200 kV, 300 kV. In some cases, if you want to avoid defects, people also use low kV TEM. But yeah, yes, as long as you are able to match the threshold, it should be possible not only with the E-beam, even with the other techniques.
Thank you, sir. Thank you so much, sir. On behalf of all the participants for answering all the questions and for the energetic talk. So rest of the questions, sir, can be addressed in the chat box. Thank you, sir.
Yeah, thank you. Thank you. Yeah, nice interacting with all of you. Yeah, all the best for the successful completion of the workshop. Thank you very much.
Yeah, thank you, Vishwanath ji. This is Ankush here.
Yes, Ankush. Yeah.
Yeah, thank you for
Thanks
accepting our request.
For inviting and sending me the link also yesterday. Thank you very much. In between,
Yeah,
there
thank
was
you.
some connection problem. I hope I'm able to communicate.
No, it was all good. Yeah.
Being a Saturday, I was, it's a cold here. I did not go to office. I was trying to cover from the home. I hope it was not creating any big difference or difficulties.
Yeah, it was all good and nice. And we hope to host you sometime in near future and in person in our campus. Yeah.
Definitely. I'll be looking forward. Definitely we'll meet.
Okay. Bye.
Thank you.
Thank you.
Thank you once again, sir. Now we take a short break for 10 minutes or 15 minutes. Then we will meet again. Hello, sir. Hello. Hello, Professor Michael Hutch.
Yep. Can you hear me?
Yes, yes, sir.
Yes. Okay, that's great.
Can you share your screen?
Sure. 1 second.
Yeah.
So I hope you can see it now.
Yes, sir.
Okay.
Welcome back. Now the second talk will be delivered by Professor Michael Hutch on the topic entitled Scanning Probe Lithography for Bioactive Surface and Device Functionalization. Michael Hart is leader of the group for scanning probe lithography for biomaterials and bioelectronics, situated in the research unit of Professor Ahasi Hegman at the Institute of Nanotechnology of the Karlsruhe Institute of Technology, Germany. He holds a PhD in physics and in medical science from the University of Munster after doing research on self-organization phenomena in phospholipid film generated by Langmuir-Blodgett technique during his PhD. He is now focusing on advancing deep pen nanolithography and other scanning probe lithography method for application at the interface of physics, surface chemistry, and biomedical application. In 2018, he received the high-end foreign talent of Shanxi province at China and currently become a honorary faculty member at the Center for Nanotechnology, IIT Guwahati. With this brief introduction, I request Professor Hart to kindly begin with his talk. Over to you, sir.
Okay, thank you for the nice introduction. So yeah, today I want to show you a little bit about our work and in particular introduce you to scanning probe lithography and with some focus on the, let's see, get the laser pointer on the bioactive functionalization of surfaces, because that is where it's in particularly well suited. And you will see. So let's start. First, a little bit about the topics. So as I said, I want to introduce you to these different techniques that are related to most of them to this technology that's called dip pen nanolithography, and they come all under the umbrella of scanning probe lithography, which means basically that you have a probe and you scan it over the surface to create your surface patterns or do the functionalization. So first of all, what are we looking at or what are we aiming at? So I turned here from our world to the micro realm. So the idea behind it is to give you some idea of what are we doing now. I mean, most of you are familiar maybe with this, but I guess it can't hurt to remind you all of what kind of length scales maybe are involved. So if you look here at one of Germany's famous fable animals, the Bremer Stadtmusikanten, so they are the city musicians of Bremen. So and it's a story for children about these animals, and it's so famous that they got like a statue here. And if you can see here, it's around 2 meters high. No? So here is a person next to it. So it's like our standard realm of length scale, let's say, where we all live in. On the right side, you see a similar statue of the same animals, but if you look here now at length scale, that's with an SEM, so it's only 10 micrometers. So the whole thing is maybe around 100 micrometer high. So this is around 50,000 times smaller than this one if you calculate it. So the question is, how do we sculpture things at this height, at this length scale? And in particularly, this is not even the nanoscale. So as you all know, we go there, we even want to go a little bit smaller. So we want to go here around in the 1 micrometer to 1 nanometer scale. And if you compare this again with the natural world, let's say, you can also see that a lot of interesting biological phenomena start at exactly this length scale around 1 micrometer. So if you come from the bigger side here, you have the things that are around us, like birds, ants, and here you go to the really, really small animals like a flea and a human hair. So this is like in the upper micro world. And the statue that I just showed you, that would be located somewhere in between here, about a hair size or the size of a flea. And then if we go a little bit more down into the length scale, we come into the realm of bacteria, single cells in humans, and viruses, and then even going down to the micromolecules like DNA or real molecular structures. And this is in particular the realm that I will talk about today. But the same techniques apply also down to the nanoscale, where you can also use them for manipulation, as you have also seen in the previous talk. So this is probably currently the smallest kind of signature or so you can do, because it's basically made from more or less single atoms. So each of the points is single atom. And you can see, if you can read this, you are too close. That's certainly true if you look here. So it's only like 13 nanometer is the whole image width here. The question is now, how can we manipulate matter on such small scales? I mean, our toolkits to shape the world, as I said here, they start from the very big ones, like these machines. This is like to get coal out of the earth. And so these are very, very big, because if you look at it, this is like a standard bagger that you would see, like a standard construction vehicle. And the size of this to this, so you see the shovel alone here is bigger than the standard thing that you see here, that you will maybe all have seen already on construction site. So it's for us, or we developed already a lot of machines that can shape the world in the bigger scale. And in the scale around us, we have the most tools, I would say. So this is the regular world where you and I even do maybe garden work or whatever, and there is a lot of tools how to shape our environment with this. If you go to smaller scales, like on millimeter scales, there is still tools that basically we just use our hands and give them finer, sharper ends, let's say, so that we can also shape things even smaller than this. And if you are very skilled, maybe you can do with such tools, do lithography, if you want to name it like this, on even a sub-millimeter scale. So maybe you have also seen people that can carve something in rice or corns, or like in very small grains. But then how can we go even smaller? So what do we have when we really want to go to the nano world and to move, like, let's say, single atoms around? So for this, we need to take a short step back. And I would like to introduce you to the basics of what's called the scanning tunneling microscope, because this is basically the microscope version of where all these techniques that I talk on are coming from at some point. And for that, I would briefly remind you of the tunnel effect. So this is a quantum effect. That means that if you have an energy barrier and you have a wave, a quantum wave coming from one side, and it should not be able to cross the barrier because energy is too low, there is still exponential decay of the wave function. And the wave function has still some non-zero chance to come out of the other side. If you look at it less abstract, it means that in classical physics, you would have an impenetrable barrier by this, and the tunnel effect allows things like electrons, or in this case, even a line, that's also possible in quantum physics, just much less probable, because it's such a big object to tunnel through, and of course that could cause also kind of problems. But we can also do positive things with it. And this is particularly if you use a tunnel effect between two conductors, let's say. So you have like a metal on one side, metal on the other side, and there's a small gap. Then this gap, in principle, would also have the blocking effect, and no electrons, no current could run. But by exploiting this quantum effect, if you apply a bias, and there is a possibility then for a directed tunneling of electrons through the barrier, through the vacuum here, to reach the other side. And this is actually exploited in the so-called scanning tunneling microscope. So there is a sharp tip brought near to a sample, and it's not touching the sample. But if you apply voltage, then still here we have our gap that can be tunneled through, and then some electrons could tunnel from the sample to the SDM tip. And the trick is now that this is the amount of tunneling, because you have an exponential decay here, is very highly dependent on the distance. So you see here the current goes with the distance here exponentially, and all the rest can be seen here as a constant. And so it's all dependent on the distance here. And so that means that you can very nicely monitor a distance between tip and surface. So you have a factor of 10 reduction here for the current for each 0.1 nanometer. So that's really like for atom thickness difference here. And the scanning tunneling microscope now exploits this by taking the tip, scan it over the surface, and monitoring the current. And this means that then line by line, you can come up with images of the surface by means of the current density. And if you can see here, so this is like one of the very first things that came out of a scanning tunneling microscope. That's the surface reconstruction of silicon 111. And they could finally reveal that you have this 7x7 surface lattice cell, let's say, for the reconstruction. Nowadays, it got not very much, let's say, advanced with this. So the resolution and everything got even better. The stability got better, and you can even do images like this from carbon nanotubes. So at the same time where Gerd Binning and Heinrich Rohr got the Nobel Prize, that was like in I think 1984, for their design of the scanning tunneling microscope. At the same time, also the so-called AFM came then up, and that uses the same principle, but can also work on non-conducting samples. I will show in the next slide. What's also happened in parallel very soon, and this is actually also how this kind of images are prepared, is that the people used the same thing for manipulation, as like manipulating atoms on the surface, and you can do it by going to an adsorbat atom, apply short pulses that could either carry the atom to the tip or remove it again from the tip, and in between move the tip to the places on the sample that you want to desire. So as I said, the one drawback of this is that you need a conducting sample. So what was then also very soon developed, as I said, like in the 1980s, was the use of the STM to induce something, or to develop something that's called now atomic force microscope. And this was basically done by first using an STM to now monitor the movement of an AFM tip. So I hope I can get that to work. So now this is video. So here you can see how the tip movement induces the difference here now to the other tip from the STM. And this distance, as I said, now it changes a lot the current that you can measure here. So by this you can now measure the deflection of such an AFM tip. And this is now independent from surfaces conductance, because the tip can also be bent by a non-conductive surface. And that would mean that now we can monitor the tip bending instead of having monitoring of a current. And this current independency allows us then also go to non-conductive surfaces. So in modern AFMs, this is not done anymore by a STM. So there is not this double feature, let's say, but modern AFMs usually use a laser that is reflected from the AFM cantilever and measured far away on a photodiode. And by the modulation of this laser, you can also monitor again the replacement of the tip. So that means, or the displacement of the tip. And so that means that we can again scan over a sample and get our image done. So why did I tell you all this? This is because the AFM, the modern AFM, is basically the root of all our scanning probe lithography methods. And today I will talk about mainly these methods, as I said, like the three methods of like dip panel lithography, polymer pen lithography, and different kind of spotting and scratching technologies. And you can see that they are also nowadays in machines that are more or less like desktop machines. So you can see here that's a normal computer monitor. So it's not such a very big machine or so you can really have it on your desktop. And it's kind of easy approach to nanolithography. So with that, let's go to the first technology that I want to talk about. This is about nano scratching and so-called nano shaving. So what do we see here? Here I refer back to what I had said at the beginning, that the ideas that we use here are quite old in principle. So you can see here the old cuneiform writing that was done in the Middle and Near East. And so on a clay tablet, and you use a sharp tool to put in your signatures, your letters, let's say, on the surface. So we can do the same thing, but going now from the centimeter millimeter scale to the micrometer to nanometer scale by applying these sharp tips that are usually used in the AFM. And we just not use them for imaging, but we will use them for manipulation on the surface. And this is also already then the first method that was also very early on used or exploited. And this is in particular this nano scratching, nano shaving approach. So here you can really think about for nano scratching that you take a substrate, you bring your tip to the surface and you press much harder than you would for imaging, so that the surface gets really exploited or really exposed to a comparably large force, maybe in the nano to millinewton scale. And this allows then to modify the surface by scratching, or when you do it on monolayers or like self-assembled monolayers of molecules on the surface to remove single molecules, then it's also sometimes called nano shaving, because you're really only taking away the first round of molecules here. And this allows you, for example, to backfill with other molecules. So to create like different chemical contrasts on surfaces. So how does that look like? I showed here, or I show you here, like two images that where you can see the influence of substrates also on this. And you see already a difference here between the two. Here there were lines scratched by the AFM and a square. Here simply basically the same is done, but you see that there is not really straight lines, but they widen a bit. What you can also see is that the scratched out material, of course, needs to go somewhere. So you can see it here on the side. And if you look at it, you can see also here that the scratching depth is seems in the first run here to be a little bit higher, though it's both polystyrol as a sample volume, as a sample material. But here it's easier to measure right now because here the steps are wider. But you can see here already the substrate also. So this is a silicon oxide that is harder, much harder than the polymer on top. So it's like a straight edge below. What you can do here on the polystyrol polymer brush is that you can afterwards also make a sonication to wash away the debris, so what was scratched out. And now you can also see here that you reveal a very nice pattern, and you can also have very fine details, what's not really done anymore here on the spin-coated polystyrol. And if you look for close-up, you can also see that here you have fairly high, like about 100 nanometer resolution here at the end, where you can expose the substrate here. So what does make this difference? Why is this giving you some clean lithography? And here you have this kind of widening of the lines. For that, I would briefly show you what polymer brushes are. And the polymer brush is basically similar to a regular polymer, but instead of the lines being, instead of the polymer chains being just entangled with each other, a polymer brush is bound to the surface where each of the polymer chains grows either from the surface or is, when it's pre-synthesized, grafted to the surface. But in both versions, you end up with a polymer brush, and the defining feature is that these lines are, that the chains are connected each covalently to the surface. So if we now compare then the two materials, so we have polymer brushes on the one side, they're all bound to the surface, and on the other side we have a spin-coated polymer, which is more like a maybe spaghetti-like structure. Then it becomes understandable why we see this different, and it holds also true for different kind of polymers. So here are like 3 different polymers, and you can always see that the spin-coated polymer will have a widening of line, because when you scratch through it, you can understand or can imagine that you drag along these entangled polymer chains. And so by this, you drag along more and more material and you widen the material, while the polymer brushes, as they are kind of more neatly constructed and they're more stable to the surface, they really only scratch around a little bit out of this, and you have your fine confinement or your high fidelity in the pattern later on. It's a little bit like maybe a mixture even now of nano shaving and nano scratching, because here you could also say, okay, you're removing molecule by molecule. Also, it's a macromolecule now here, so it's a very long chain, let's say. You see it span over several nanometers in this case. You can parallelize this. And so instead of only using one tip, you can use 1D arrays of tips, as you can see here. So now they're in contact, they're bending a little bit. That's why they change in color. And finally, you can write a pattern. So you can see here maybe the little bit dark things. And if you look at this again with AFM, you can see here different logos from University Münster and the KIT. And again, you can scratch fairly nanometer sized films, like here up to 50 nanometer films. With this kind of arbitrary patterns. You can also use this to get into some proteins, for example, that can assemble directly on the scratched areas, because now you have a chemical contrast between your polystyrene brush and these scratched areas. So here, this was done with a fluorescent protein, and you can see that while the polymer brush around it is fairly dark, you can see here still it's selectively attached to the sites that were scratched. And so by this means, you can again get your bioactive patterns. So up to the next technology. So now I will talk about this dip-pen nanolithography. And here, you have a similar old ancient concept, let's say. In this case, it's like a writing of monks on scribes, and they used so-called feather kills or like small scribe tools that you could dip into a chemical and into an ink and then write to the manuscript surface. And again, we will now mimic the same thing with an AFM tip. So on this, I will shortly talk about what is a self-assembled monolayer. I already mentioned this once. It's basically a self-organization of most of the time like linear molecules. One very famous system for this is a thiol system. So you have a thiol and a hydrocarbon chain. It can have different chemical functionation at the end, and when you bring it near a gold surface, they will attach to the surface over the sulfur here. And you will end up with a kind of, let's say, nano or like a molecular crystal that grows in 2D on the surface. So what is shown here. So at some point you will get a very neatly, tightly ordered layer under the right conditions. And by this, you can, of course, change the surface chemistry to almost arbitrary things when you can go on here or change here the functional moiety at the end. And this led to a lot of interest in self-assembled monolayers, and they were also frequently imaged with AFMs. And this led to, in the late 90s, this led to the observation that if you scan such a monolayer, then sometimes at the end you end up with material from the monolayer attaching to your tip. So a clean AFM tip maybe looks like this. You can see very neat, everything is tidy. And afterwards it can be covered in such thiol material because it's just attaching to the outside of the tip. And this leads also to observations that if you go with a dirty tip to another place in the gold surface where there was no organic monolayer before, then afterwards, after scanning it with the tip, you also see growth of self-assembled monolayers there. And then the idea came up, okay, we can also do this on purpose. So we take what was once considered like a dirty tip and really on purpose ink it with the thiols. And then if you scan a surface, you can see you can order here or even orderly transfer these kind of monolayers. And this led then to the advent of the so-called dip pen nanolithography. Let me start this. So what you see here is now how that can be exploited. So we move in or zoom in on the AFM stage. And here you see the AFM tip, cantilever tip, and the tip is now covered, for example, with a thiol. And if you bring it to the surface, you can now write onto the surface really like you would write with a feather quill, let's say. This can also be parallelized again. So you can write different patterns with different tips in parallel to speed everything up. And now the whole image is transferring to a real AFM image. So what you see now is not anymore an animation, but this is a pattern that was really created. And you can see even here, it's already like each of the letter, these lines, they are only 65 nanometer wide. So again, you go to a very, very high resolution. That's well in the nano realm. So if we go back here, you can see here, this was like coined the term dip time nanolithography by the Merkin Group in 1999. So a few years later, and they could really nicely show here the different deposition of self-assembled monolayers in arrays or in lines by bringing the AFM tip over the gold substrate, and you can see that a water meniscus is building and then the molecules transfer over the surface. This also gives you two obvious control parameters for this. One is the contact time. So the longer the tip is in contact with the surface, the more material will transfer. And the other thing is about the relative humidity. So if you have a high humidity, then also usually for hydrophilic materials, more material can go from the tip to the substrate because the water meniscus is bigger. This is, in the case of thiols, more well good theoretically also understood because you can model it with a 2D diffusion model. So it's a regular fixed diffusion. And This means that you can think of the AFM tip as a kind of a point source, and the molecules come down to the surface and give you a 2D diffusion. So this is why they grow also in this circular fashion with time. So yeah, now the thiols are not the only ink type that can be used in dip-pen nanolithography. So basically it can be also other things than thiols, and as long as they still go over such a diffusion process, we usually call them diffusive or molecular inks. And this works like I just described, that you have a dissolution from the surface of the tip into water meniscus and assembly on the surface. And you usually end up then in these kind of self-assembled monolayers that are highly localized on your substrate. In terms of more liquid viscous inks, that could be, for example, polyethylene glycol or like glycerol or any other non-volatile inks. They will go over from the tip to the surface in terms of a viscous flow, and this is much harder to describe. So because here you would go into the realm of hydrodynamics. But basically what you end up with is that you then deposit small droplets on the surface, and the shape of these droplets is then highly governed by the surface energies, also by the surface tension of the liquid and the surface energy of the surface. So there are also different tricks, let's say, how you can also get other materials to the surface. So here again, the classical DPN, what they termed here classical, is like the diffusion model over the water meniscus, but you can also use all kind of solvents or other materials. So the liquid DPN, as I also showed in previous graphs, and you can also include materials into this. So then you would say like, okay, you have a material that you want to transfer, and you have a matrix that's maybe carrying the material or a solvent, and this matrix helps with getting stuff down to the surface. This is, for example, very helpful if you want to deposit nanoparticles that will maybe in itself rather stick to the tip. But if you combine them with other materials like a glycerol or like a more viscous ink that can draw them to the surface, then you can also write these. So what's also a nice feature of DPN is that if you go for parallelization, you can also do so-called multiplexing. For this, we use like microfluidic so-called ink wells that you can fill with the desired ink by a pipette in a, you see it's still 2 millimeters, so that's addressable by hand by a pipette. And then there are microfluidic channels that take ink from here to a place that lines up with the separation of your tip array. And then you can dip your tips in parallel into these small containers here. And by this, the tip array itself can carry, for example, different inks on different tips. So this has happened here. So here you see an inkwell, and you see there are 2 different kinds of fluorescent inks. And here each 4th tip was covered by putting it in here. It's actually the array that you can also see here. So each 4th is getting in a microchannel, and you can see that they can now carry different inks. And this means that you can in parallel write here, also the black thing here, this is a pyramidal tip. And in parallel, you can write these different inks next to each other. You can also go from 1D to even 2D arrays. This is shown here. And then you can go really also with DPN to fairly high surface areas. So you can see here how it's structured, 1 by 1 centimeter surface with this kind of dot arrays that are in the range where they can interfere with optical light. So it's like an optical diffraction mirror, let's say here, or a grating. And you can see here nicely where the nano pattern spans here over this very wide area with this. What we in particularly do to go back now to more biological materials is to use the DPN also with biomolecules. So in particular here for phospholipids. And here you can see some phospholipids, they all can carry different functions. So you have here, for example, fluorophore or also binding motifs. And they can also be brought onto the surface, and then they assemble into kind of this neat biomembranes. And why we do this, or why it's interesting, is because of the certain biological purposes of these lipid molecules, because they are the main constituent of a biological lipid membrane. So in all of our cells, you have a lot of different membranes, and all of these membranes, and in particular here the outer membrane of a cell, are constructed by lipid bilayers. So you take these kind of molecules, and because they have a hydrophobic chains and hydrophilic head groups, in a water medium, they will self-assemble to these kind of membranes. And the biological membranes carry also all sort of different functional molecules that allow the cell to basically to live. So you have channel proteins that control the in and out through cells. You have transmembrane proteins that usually do kind of or are involved in signaling. So they detect either something on the outside or signal something to the outside. And you have a lot of glycoproteins here that also have various different functions, from signaling to anchoring for stuff to enter the cell, or also to attract or modulate other cells, like immune cells, to alert them about what's going on in the cell. So what we try with the DPN is then to make easier versions of this for interfacing or also for sensing purposes. So this is done more or less in this style. So you can see here again a tip array writing, in this case, like squares to the surface. And if you look at it at a molecular picture, that would work like similar here, that you have the tips, the phospholipids, and they go from here to a monolayer on top. If you do that in air, then because of the energetic reasons, you don't end up first with the biological membranes, but more with the kind of inverted membranes. So here you have the tails out configuration, and the hydrophobic chains are going outside to the air. If you have a hydrophilic substrate, the head groups will go here like this. But as soon as we put them into a buffer solution, also like transfer it to a liquid environment, then they rearrange, and we will end up with supported lipid bilayers here in this case that have the biological tails out version. And then, and this is an important step, we can use the functional lipids, for example, here the biotinylated lipid as a binding motif that can show a very high affinity to another protein called streptavidin that will bind to this and then allows us to bind additional stuff, for example, functional antibodies or whatever proteins we want to show to other cells towards these kind of membranes. So what you see here is also like that we can also functionalize, for example, 2D materials with it. So to bring it also in this context of the present workshop, it can be also used like for this kind of electronic application. So here you can see a tip, and we can really, by microscopic images, we can address, and you can see here lipid patches that were written actually on the graphene flake here, and you could basically exploit it. You can also here, by the way, see that there is fluorescence quenching on the graphene. So this also tells you that the membrane is small and is like in a very vicinity to the graphene and can electronically interact. So the fluorophores in the membrane were quenched, and you don't see them in the fluorescent microscope anymore, while they're for sure here. If you look at AFM, we can see also, again, these layer structures that I talked. This is all done in air, and you can see on a clean graphene that's more hydrophobic that you have like only a double layer, so one layer. And on the silicon oxide, you have this wetting layer, the single layer, and then the double layers on top. And this is also in a molecular picture, let's say, confirmed by molecular dynamics. So for time reasons, I don't want to go too much into this, but you can see that we have this control over the configuration by having either more hydrophobic or more hydrophilic surfaces. This is what I wanted to say. So A similar approach is that's connected to this is the microchannel cantilever spotting. So this works now not as a fountain pen, but in a more controlled way, like more like a pencil, let's say. And here you have a similar approach, but instead of having again the millimeter scale channel here, you come with a reservoir and a cantilever that is more on the micro realm. So, and then the ink that you put here can flow down to the surface and end up on the surface for defining small droplets. So here you can also see how it looks then in the machine. You can see here we have a 150 micrometer scale. So this is the channel. You can see here the cantilever and the microchannel within. And it's hovering over a microarray that was just spotted with the sample. So you can see it has a lot of different droplets on the surface. And this is particularly neat because now you can do chemistry also in this droplets. No? So they are femtoliter sized and allow you to let wet chemical reactions happen in these small kind of reaction vessels before you wash it away and you end up, for example, with the immobilized molecules from these reservoirs. You can also do multiplexing here. So that means here again, for 3 different fluorophores were spotted next to each other. So it means you can have very tiny or neat arrays of different materials next to each other that are not that easy done with standard lithography methods. This can work either by what's done here by just subsequently spotting different materials, but you can also do it in arrays again. So here is like a chip that has different compartments, and you could fill different inks into these compartments, and then you end up with different inks in your different microchannels, and you can in parallel then spot this, what speeds it also or nicely speeds it up. We can also do protein binding again to show here. So here's another array spot, and if you look at it at fluorescence, you will see that only each second spot is visible in the fluorescent image. And this is because there are 2 different materials, though the color is the same. But in fluorescence, you can see that only here we have fluorescent material, and in between here there was a biotin azide spot. Also these droplets that you don't see here are biotinylated now. If you wash everything away, then in bright field you will not see anything anymore, because there is only a monomolecular layer now remaining. But if you look at fluorescence, you will still see the nice array as before. You can see that it's a little bit less fluorescent, but that's because now we're really looking at only a monolayer of the molecules and not anymore as a whole droplet. So if we then go on and incubate labeled strapped up into it, then all in a sudden also the drops in between light up. This is again because now we have the biotinylated molecules here on the surface, and the streptavidin binds to it, and then you can see again the full array. And of course we can also do that again multiplex. So here it's also like with a protein spot and 2 different fluorophores, so as before. We can use these things, for example, for selective cell adhesion. So that is what you see here. So each of the droplets here now is or has 1 cell sitting on it. And yeah, finally you can end up with this nice bioarrays for this. So what I will now show you is then a combination. So this is like a kind of combination of the microchannel spotting that I showed before and the AFM, because now instead of having an open channel, in the group of Zambelli here, they developed like hollow AFM cantilevers, and they call this technique fluid FM. And this is also kind of nice thing. In principle, they built this for being able to inject things into cells. So to use it like a syringe, so that you can use it in liquid, because it's a closed system. You have a tubing that is can apply pressure to it, and then you could inject things through a cell membrane into a surface, into a cell. But then this was also very quickly exploited for lithography means. because instead of instead of using it in the cell environment, you can also deposit, for example, in this case, fluorescent microparticles on the surface. And you can see also here again, you can have line patterns, and so you could do patterning in liquid. And we also used this again for the lipid writing. And this was done in particular here, with writing for vesicles, let's say, onto surfaces. And you can also build the bilayers and directly in water if you would like. As I talked about the lipids already, one other application that you could use here is also to use it for polymer inks, and in particular interesting for us, and this is also like really ongoing work in our group, so that we use UV curable polymer inks to use it in a kind of a layer by layer fashion to make really 3D printing possible with it. So micro 3D printing. So again, here we have different writing parameters you can see, and the writing parameters also applied for different surface features, also like different surface energies. So again, writing velocity, contact time, and in this case also again, you can see the height of the structures is pretty different for the different things, for the different surfaces, influences this quite a lot. Again, here we would also like to biofunctionalize the inks. And here again, the biotin-related lipids or the lipids in general can help. Because now you can think of if we print such a polymer and we want to have the biotin molecule, for example, here on the outside of the polymer, one of the approaches would be like to take a surface active agent like the lipid, because again, you have the hydrophobic and hydrophilic parts, and hope that this will assemble also at the interface between the ink structure, the main structure, and the outside. And this is actually also what we observe, or what we observed to be happening. So enough of the material of the biotin sticks outside of the printed structures. So what you can see here is that we have a structure, and here we have just the polymer, or here we have just the polymer structure. Here we have polymer structure with fluorescent. And here we have the same thing, the polymer structure with the fluorescent, and the polymer structure, but now here with the biotin PE. And if we incubate it with the streptavidin, then in this case, for the biotin, if biotin is present, it can bind to the biotin. And here you have the merged images. So here you can see that the biotin-related protein is again, the streptavidin is again going to the biotin part, while the single or the pure polymer would not bind this kind of proteins. So as last thing here, I would show you the capillary writing. And this is one other thing where we also use like a small, in this case, a glass capillary to deposit liquid metals. So I just wanted to bring that in, so to show you that also there is a wide range of materials that could be printed in such processes. And if you look at it, this is again mounted on such a AFM-like structure. So we don't have any AFM tips anymore, but now this glass capillary. And this is filled with a liquid metal. And in this case, we use eutectic gallium alloys. So one that you can even buy is Gallinstan, that's made of gallium, indium, and a tin. And the nice thing is it has a melting point of -19 degrees. So at room temperature, it's already possible, and it can replace mercury, because one of the very nice things that you cannot do with mercury, but that you even could do with Gallinstan, is to just put it on your hand, because it's really non-toxic, and so it's a very nice material, let's say, to work with. And it's also highly conductive, which makes it interesting for printed electronics. And this is also where we use it. So we can, with this technology, now print different lines of this. And you can see the line width is correlated with the capillary size. And as of an oxide layer that is building around it, you can even have freestanding 3D structures. So it's a very nice, flexible material. So this is still liquid and there's no curing required. But still, you can have some things like this kind of intersects. We showed also here already that that you can have applications in printed electronics with it. So basically, for example, you can print diodes or transistors with it. And here the liquid metal is used for kind of connecting the other functional materials with it. And you can print, you can combine it either with conventional printing methods like inkjet printing, but you can also deposit the other materials also with capillary printing. So for example, here the indium oxide is also deposited with the capillary printing. Good. So this brings me to the last chapter. So this is about the polymer pen lithography. And again, we look for the inspiration in the ancient world, let's say. So in this case, it's from stamping. I took here like one Chinese stamp. I guess there's one of the oldest cultures, let's say, to use stamping. Of course, many other places on the world also used stamps, like wooden stamps or so. And again, we try to miniaturize this and give us control over it, even in the micro or also even in the nano realm. And this leads to this so-called polymer pen lithography. So it's a kind of combination of micro contact printing, where you may be familiar with, and the dip pen nanolithography. And what it brings in particular is a massive parallelization, because now you attach a polymer stamp to the piezo scanner of an AFM, and you have now many pyramidal features here on such a thing. So you can see here a wafer size that's filled with this. And you can see here with a 40 micrometer pitch, for example, you can have several 10 of thousands of these structures on a square centimeter. And they all have a fairly sharp tip still. So it's like a 60 nanometer in this case. And this allows you then to print together features onto the surface. So here it's shown how such a stamp is made. This is another nice thing, because if you think of how do we get these pyramidal features, it can be even done automatically by anisotropic etching. So if you come with a silicon master that you use and you apply a photo mask to it, then afterwards you can do a selective etching with KOH. And automatically pyramidal features will grow when the right silicon crystal structure is exposed. And now, if you do this is only needed to be once, then you have the master here. And this master can be always put or replicated with a elastomer. As most of the time we use PDMS with a glass support to it. You can take it out and cure, peel off, and you have your pen or your stamp for the polymer pen lithography. And then you can use it again. So you can always start again from this step, fill it again with elastomer, put a glass slide on it, and take on of the next. And it can do this for hundreds, when not even thousands of stamps. So in this case, it's also kind of a inexpensive way of producing your probes. Then, as you've seen here already, you have the contacting here of your stamp to the surface, and this will I can repeat this here, yeah. And then the tips are touching to the surface, and if you only touch once, you will get only one feature per pyramidal pen. But if you touch several times, then of course you can more or less bring arbitrary patterns to the surface by just bringing together the dots so near that you receive whatever pattern you are aiming at. So also here we have different writing parameters. So one is the force and one is the contact time again. Now here we have force also as additional writing parameter, because if you press more and more, you will deform the tips, because now they are flexible. As like I said, it's an elastomer like PDMS. And this leads to bigger and bigger features the more you press, because you just simply press harder onto the surface. And this is also reversible here because the tips are not damaged, or at least not damaged too much by this. So you can see if you apply more pressure, features get bigger and they get also smaller again if you replace it. Then the contact time is still like a normal DPN, and this is why you also get the circular, like the diffusive pattern here with different contact times. With longer contact times, you get more and more features. Again, we can also do multiplexing with this. And this works by applying a subsequent stamping. So if we have a 2-color stamp and we stamp our patterns only once, you get your pattern in one color or the other color. But now we can move, because of the precision of the stage, with a second color over the first color, and we can get these kind of multiplex patterns. There is an offset correction needed, but then you can have nicely aligned patterns. And of course, that's not only with 2 inks, you can also do it with 4 inks or even more. It all depends now on the size that you can reliably move your stamp to it to achieve your target pattern. So we can achieve very large patterning here, also over square centimeters. Here we look at an area where the 2 patterns merge together, and here you would have now millimeter to centimeter scale patterns of this kind over the rest of the substrate. Here, for example, also just a multicolor with a lipid molecule, and you could think like that each of this could be, each of this area could be an experiment for one cell. So you could have, for example, cell polarization experiments with different compounds. So this is typical applications of this. We also can use it for DNA patterns, and this is also what we often use it for, like again, to bind different DNA sequences in something called DDI. So there you could have functionalized DNA strands that carry, for example, certain proteins or growth factors in this case, so it can induce certain cell activities of these kind of patterns. As I mentioned, and particularly interesting is that we have this large area prints here. So it's fairly easy to cover whole cover slips with it, and you can use microfluidics, for example, microfluidics caps then without need for careful alignment or so. So you can just put them over the cover slips, and now you can do experiments, for example, in 6 channels in parallel on such surfaces. Here it's an example of a model allergen, where then you can monitor cells, immune cells, how they react to the model allergen here, and you can see that they align certain receptors with the array. Mm-hmm. Yeah.
So we would like to remind you that time is almost over. So could you?
Yeah, sure. I'm almost at the end. That's fine.
Yeah. Thank you. Thank you.
So the last thing that I show you, this actually the last thing is here also so-called beam pen lithography. And I put this in as an example of that now these kind of technologies can also converge. So beam pen lithography is basically like a convergence of polymer pen lithography, what I just showed you. So we use a similar arrays here, and it has aspects from photolithography, because now here you cover your stamp with a gold layer, and then you bring it into the surface. The gold layer is, of course, more brittle than the polymer itself. So you can open up the small apexes on the surface here of the pyramids. And this allows you to, if you shine light on it, to bring a very, very confined, you can see it's even sub-wavelength confinement of the light to the surface here. And this can be even combined with so-called digital mirror devices, so DMDs. And by this, you can turn on and off different light on these pyramids, like different pyramids are on or off in parallel. And this allows you on photoreactive surfaces to also have large area patterning still with a sub-micron resolution, what's also here demonstrated from the Merkin group for like chemical formulas in form of this Volpra. So with this, I come to my summary. So the general things about scanning probe lithography I hope to show you are that they are maskless. It's an additive technology, and they have mostly mild processes. And in particular, you have a very wide range of materials that you can print with them. And here I just have a small overview over the different resolutions and different drawbacks, let's say in speed, also high speed, low resolution. And yeah, if you want to have a look at it further, you can always look at our website. This is particularly a paper that is focusing on these kind of scanning probe lithographies. And yeah, this is basically what I hope to convey to you today. We have a lot of applications. So just to show this, if you contact me, I can bring you to your like what you're most interested in, either more in the electronic part or more in the biology part. And we also do different device functionalization, where you can also see here different devices that could be functionalized via these techniques. But for this, I would say just contact me. With this, I would thank you for your attention and show also here the people that are involved in our work and refer you to our group homepage if you want to know more about it. And of course, I'm also open to answer your questions.
Thank you, Professor Hart, for such an informative talk. Now we begin our question and answer session for this topic. So our first question asked by Franco: how stable is the nano ink, and what about the adhesion strength on any type of substrate?
That's a very good question. So this is really dependent on the ink itself, let's say. So in the case of the dip pen nanolithography, for example, if you have these thiol patterns, or if you have, I didn't show that, but you can also have like click chemistry patterns. So then you covalently bind to the surface, and these patterns are very stable. No? So you can do washing with them, you can do whatever that does not destroy the whole surface, and they will be stable. If you have things like the phospholipids that I showed, they are just physisorbed to the surface. So they're really just lying on the surface. This is still surprisingly stable. So we can experiment in water with it, because the first supported lipid bilayer still likes to stay. But in principle, you can wash them away, for example, with the right solvent. So if you go with chloroform onto it or so, something that solves the lipids, it will be easily removed. And then there are yet other functionalities, like if you would have like let's say water soluble molecule and you just put it on the surface, that might be even removed by simply washing if it's not attaching to the surface. So to sum up, it all comes up, the stability comes very much up to the surface chemistry.
Thank you, sir. The next question asked by Rameja. So the question is, what is the smallest size that we can achieve with this tip? Like, he's talking about the resolution. And the question...
Sorry, I didn't...
What is the smallest size that we can achieve with this tip?
Yeah. The smallest sizes, also there is two different things. One thing is what we can regulate from the tip. This is really very precise. So you can, this is like basically what you can do in an AFM. So you could go into sub-nanometer even, like to measure. And you can address as well in this nanometer, even maybe below nanometer scale, for the registration, also like for which part on the substrate you can apply to. What we can achieve in writing, this is a little bit different, because this again depends a lot on what kind of ink you use. Also if you have for example thiols on gold, as I showed you, this can give you a fairly high resolution, also like around 50 nanometer. But if you have, for example, an ink that's more prone to spread on the surface, and also if the surface, for example, is very hydrophilic and so high energy and likes to attract the ink that you deposit, then this can go up. For example, the lipid resolution with the phospholipids is around 100 nanometer. And if you want to deposit, like, let's say, a water-based ink, then maybe